we looked at pulleys, how they work, and kind of the general idea, but we haven't really done any examples, so this is going to be a video of pulley examples. First, let's try the one that I started to do. I've got a block like this. Let's give this thing a mass of 5 kilograms. And we'll do a triangle mass over here. We'll call this thing 2 kilograms. We're going to connect them by passing a rope over a pulley, and this block can be on a table. This is a frictionless table, of course, because we haven't started talking about friction just yet. It's coming. I would like to know, find the acceleration. Maybe I can find the tension in the rope. And maybe I can say, when I release this thing from rest, find how long it takes to reach the end of the table. Which means we need to know where the end of the table is. So we will say from here to here, that's the end of the table, can be 2 meters. There's our setup. Let's get moving. To do this problem, we're also going to have to make a statement that this triangle is able to move down a long way. So maybe there's a big hole in the ground or something. It's able to move at least 2 meters. So let's see, I'm going to draw a free body diagram for my block. My block has acting on it gravity, that's the easy one, and a normal force from the table. It has a rope attached to the right side, and that's it. There's nothing else. So I'm going to say to the right will be my positive x direction, up will be my positive y direction, there's my axis. Okay. Guess we are crossing off part of the axis. That's okay, and there is the box around, which crosses off a different part. For my triangle, I have just 2 forces. I have an M2G. By doing this, I'm saying this is item 1 and this is item 2, but I'm sure you caught that already. And I have tension going upward. And it's the same rope, so it's the same tension. If this pulley were not ideal, if there were friction, if it had a bunch of weight or anything like that, then those tensions would not have to be equal. But one rope passing over an ideal pulley, the tension is going to be the same everywhere. I have to draw an axis for this. Now what I had back here was a positive x-axis that pointed to the right. That then passes over my pulley to point down. So this is going to be my positive x-axis, and this is going to be my positive y-axis, which is just perpendicular to x. And now I have a free body diagram for this one. I'm labeling these with my 5 kilograms and 2 kilograms just so that I don't have to go back and forth very much, or at all. I'm going to start with the box. If I look in my y direction, I see that my normal force and my M1G have to be equal and opposite. This thing is sitting, this is not because of Newton's third law, this thing is sitting on the table, so if N were bigger than M1G, then the box would start lifting up off the table. That doesn't make sense. If M1G is bigger than N, the box sinks into the table, and that doesn't make sense. These two are going to have to cancel if we're staying on the surface of the table. which we are. So then in the x direction, sum of forces in x, I have just tension. That's the only one. It points in the positive x direction. So that's going to be equal to mass times acceleration, because that's what my sum of forces is always equal to. That's what the right side of my equation just is. That's it. Two unknowns. Not a lot that I can do with that. Now I'm going to look at my triangle. There is nothing going on in the y direction, but I can look in the x direction. A big thing to note back here, this was an acceleration in the x direction. That's why it's so important that these axes are linked. So I'm going to come back to this. Over here, in the positive x direction, I have m2g. In the negative x direction, I have t. And together, that's equal to mass 2 times acceleration in the x direction. Here's where it's important. These tensions are equal. These accelerations are equal, which means I have a system of two equations with two unknowns. I'm going to take these equations and add them together. When I do that, the left side becomes t plus m2g minus t, and the right side becomes m1ax plus m2ax. T and t cancel. I'm going to factor out this m2 over here on the right, or the a on the right. So the left side becomes m2g, and the right side becomes m1 plus m2 times ax. That lets me solve for ax. Ax is going to be m2g over m1 plus m2. I can plug in some values. 2 kilograms, 10 meters per second squared over 5 kilograms plus 2 kilograms, and that works out to be 2.86 meters per second squared. There is my acceleration. Next up, I'm looking for the tension. This top equation, this is a good one for finding tension. I have tension equals m1a. I have m1 and I have a, so let's do that. 5 kilograms times 2.86 meters per second squared. And that's going to be 14.3 newtons. Finally, I'm asked to find the amount of time it's going to take, if released from rest, to reach the end of the table, which is 2 meters. If I'm finding time, that sounds a lot like a kinematics problem that I already know how to solve. So I'm going to set that up. X initial, X final, V initial, V final, acceleration, and time. Starting from 0, I'm going 2 meters. Starting from 0, I don't know my final speed. I found my acceleration, and I don't know my time, but that's the one I'm looking for. Let me come out with my kinematic equations. This first one doesn't have V final, second one doesn't have X, third one doesn't have time. I'm looking for time. If I'm looking for time, I don't want to use equation 3 because time's not in there. That doesn't work. I could use equation 1 or 2 that has the variables I need. Equation 2 requires me to know V final, and I don't have that, so I'm going to use equation 1. X final is X initial plus V initial times T plus half A T squared Moment of Dread says that looks like it's going to be a quadratic equation situation, but that's until I start crossing things off. Those go away, so I get x final equals half a t squared. Solving for t, t is going to be 2x final over a, all under a square root. So 2 times 2 meters over 2.86 meters per second squared. And I'm going to square root the whole thing. The time that this takes is 1.18 seconds. And that's the whole problem solved. I will add, the first two parts of this problem were kind of the newer portion, where we said, let's find the acceleration, let's find the tension. The third part was really just a way of tying these newer concepts together with something that we've been doing before, so that you can kind of see how those pieces fit, that we are just adding more and more tools to our belt. That's all we're really doing with this.